Hi everyone, welcome to Go Classes. So, in this lecture, we will study deadlock handling in the transaction management. From the transaction point of view, we will study what is deadlock handling, how to handle the deadlock, how to prevent the deadlock, and if the deadlock has occurred, then how to recover from the deadlock. Okay, so all these points we will study: deadlock prevention, deadlock detection, and recovery. Okay, so this is our topic for this lecture. So this is from transaction management point of view. The same topic you will also study in the operating system. In the operating system, this deadlock handling you have already seen, like how to prevent the deadlock, how to avoid the deadlock, and how to recover from the deadlock, how to detect the deadlock. Okay, so all these things you have already seen in the operating system. But from the DBMS point of view, from the transaction management point of view, how to handle the deadlock, that is our chapter, that is our content for this lecture. So we have already seen that in this type of situation, you can create deadlock is possible in the two-phase locking. In the two-phase locking protocol, deadlock is possible, correct? Like for example, if your transaction T1 is right X, right Y, your transaction T2 is right Y, right X, then in this situation, in the two-phase locking, this deadlock is possible. What you will do? You will take exclusive lock on A, then you will write A. Okay, this T1 will write A, then this T2 will take exclusive lock. But see, this T2 will take exclusive lock on B, then it will write B. Now there is a problem. What is the problem? Now T1 wants exclusive lock on Y, T2 wants exclusive lock on X, but both of them have to wait for each other. See, T1 wants exclusive lock on Y, okay, but it has to wait. It has to wait for T2. And you can notice T2 wants exclusive lock on X, but this T2 has to wait for T1. Okay, right? Yes or no? Is this clear to everyone? So actually, this this is A comma B. So you can just change it. This is just A comma B. Okay, these items are basically A comma B. Like this is item A, this is item B, this is item B, this is item A. Okay, so very simple. So there is a deadlock possibility. Now you can notice here T1 is waiting for T2. T1 wants what T1 wants? It wants exclusive lock on B. This is what T1 wants. So it will wait for T2 because T2 has exclusive lock on B. So this T1 is waiting for T2. T1 is thinking T2 will release the lock. Now T2 is waiting for T1. T2 is thinking that I want exclusive lock on A, but T1 has exclusive lock on A. So let me wait so that T1 can release the exclusive lock on A. So T1 is waiting for T2, T2 waiting for T1. This type of situation is called deadlock. None of them can progress. This is your deadlock. Both of them are waiting for each other. Okay. Now, let's see how to prevent the deadlock. First of all, what is deadlock? Let me tell you. The definition of deadlock, let's see. The deadlock definition says that if you have a system in which you have many transactions and there exists a set of transactions in which every transaction is waiting for other transaction, okay, then that is called deadlock situation. So what is deadlock situation? Remember, the deadlock situation is like this, that you have a set of transactions, you have a system. In the system, let's assume there is a set of transactions. You have many transactions. Let's assume in this system there are you have many transactions. For example, you can have transaction, let me call it transaction 1, transaction 2, transaction 3, transaction 4, and so on. So let's assume these are the transactions. Now, when can I say deadlock is there in this system? This system, I can say in this system deadlock is there. So I can say deadlock happens. When deadlock will happen? Deadlock happens when there exists a set of transactions. Please understand that we don't need all the transactions, but there exists a set of transactions. There exists a set of transactions such that in this set everyone is waiting for other. Okay, in basically every transaction in this set, wait, every transaction in this set is waiting for other transaction, waiting for other transaction to release locks. to release locks. So this is the situation. This is called deadlock situation. What happens that, let me assume that you have in your system, you have many transactions. For example, in your system, you have transaction T1, transaction T2, transaction T3, T4, T5. Okay, so these are the transactions you have. Now assume that, consider this set T1, T2, T3. Now consider this set. In this set, what happens that in this set, let's assume everyone is waiting for another. T1 is waiting for T2. Let me assume T2 is waiting for T3 and T3 is waiting for T1. Now you can notice that I can say that there is a deadlock. Yes or no? So in this situation, because there exists a set, there is a set of transaction in which every transaction is waiting for another transaction. Now T1 is waiting for T2, T2 is waiting for T3, T3 waiting for T1. So this type of situation is called deadlock. Okay, I can say deadlock is there in this system. This system has deadlock, or I can say this in this system deadlock has occurred. In this system, deadlock has occurred. Is this clear? Tell me the definition of deadlock is clear or not. Let me know. So that you can see there is a system. This is the definition. You can check it out. When can you say system is deadlocked? Look at this definition. System is deadlocked if there is a set of transactions such that every transaction in this set is waiting for another transaction in this set. Very simple definition. In this situation, you can say system is deadlocked. So you can see here that this is your system. There is a deadlock. I can say system deadlocked. Your system is deadlocked. Remember one thing, that your system is deadlocked. It does not mean that all the transactions in the system, they are in the deadlock. Okay. Are you getting my point? In the system, you have thousands of transactions. There are thousands of transactions in the system. You can have many hundred or thousand of transactions you can have. But in this system, some set of transaction, or I can say some set of transaction is such that every transaction in this set is waiting for another transaction. Then this type of situation is called deadlock. So I can say system is deadlocked when some set of transaction is like this. Okay, some set of transaction is in this format. Then I can say your system is deadlocked. Is the definition clear to everyone? What is the definition? A system is in deadlock state if there exists a set of transaction. Please understand, a system is deadlocked if there exists a set of transaction such that every transaction in this set is waiting for another transaction in this set. This type of situation will be called deadlock. You tell me a simple thing, like here you can notice there is a deadlock. This T1 dash is waiting for T2 dash and T2 dash is waiting for T1 dash. This T1 dash wants write lock on X, but this lock is taken by T2 dash. Okay, you can notice this T2 dash has the read lock. So this T1 has to wait for T2 and this T2 wants write lock on Y, but this T1 has read lock on Y. So this T2 has to wait for T1. So this is another possibility. Okay. So very simple. You can see that this is the deadlock. Your system is in the deadlock. Now you tell me a simple thing. If you already know that system is in the deadlock, what you can do? If you already know system is in deadlock, what you will do? If system is already in deadlock, if system is already in deadlock, then what you will do? Let me assume that system is already in deadlock. Then one of the transactions you will abort. Yes or no? Agree or not? If you know that already system is in the deadlock, if you already know this, that system is already in the deadlock, then definitely what you will do? Then you will abort one of the transactions. Yes or no? Abort one, or I can say some of the transaction. One, or I can say some of the transactions. Abort some of the transaction, or I can say abort one of the transactions. So if you do this, abort or kill, okay, or roll back. So roll back one of the transaction or some of the transactions, you do this. So then of course your system will get out of the deadlock. So if your system is already in the deadlock, then one, or I can say some of the transactions you can roll back. Okay, now let's see deadlock prevention. Deadlock prevention scheme. Prevention means deadlock will never happen if you do these things. Okay, what this prevention says, remember, this is the definition of deadlock prevention. This you have already seen in the operating system, what this deadlock prevention says. This deadlock prevention says, prevention, name is prevention. It says that if you do this, if you implement this, then deadlock will never happen and you will never have to check again. Okay, this is the benefit. See, if we implement deadlock prevention, if you implement this, if we implement deadlock prevention, let me call it DP. So if you implement this DP, deadlock prevention, then deadlock can never occur. First of all, that is the point. Deadlock can never occur. Deadlock will never possible. Deadlock will never be occur. And also, you don't have to check. Okay. And you don't have to do anything other than this. And you don't have to periodically check. You don't have to periodically check for it. Periodically check for deadlock. Okay, is this clear? What is the definition of deadlock prevention? Deadlock prevention means that deadlock will never occur and you don't have to check. There is no need to check periodically for the deadlock to avoid deadlock. Basically, there is something called deadlock avoidance in the operating system where you use the banker algorithm, right? Yes or no? Banker algorithm, deadlock avoidance. In that, what happens? Deadlock avoidance says that deadlock avoidance says that I will check the deadlock periodically, and just before it occurs, I will prevent it. Are you getting my point? I will avoid it. Like deadlock avoidance says that I will periodically check. After every operation, I will check. Okay. So after every request, I will check. Like this is what deadlock avoidance says. It says that after every request, I will check. And if I think that deadlock is possible, then I will reject that request. Okay. Is this clear? I will check after every request. I will check. If I think that deadlock will be possible or deadlock might be possible, then I will reject that request. So I will avoid deadlock. Okay, very simple. So anyway, this is your deadlock prevention. The deadlock prevention is saying that if you implement deadlock prevention, then deadlock can never occur. It can never occur and there is no need to check for deadlock. Okay, so very simple. You can just rest if you implement this deadlock prevention. What are the deadlock prevention schemes? In the operating system, you have some deadlock prevention schemes. What are those? Two schemes you have already seen in the operating system. Deadlock prevention schemes. What are those? The first scheme is your conservative approach. Yes or no? The first scheme, that is a conservative approach. That is a conservative approach. What is the conservative approach? Take all the locks before you start. Yes or no? Correct? This is the conservative approach, that what you do, take all the locks. Take all the locks before transaction starts. Take all the locks before transaction starts. This is deadlock prevention scheme. This you have also seen in the operating system. Okay, so I will not go into the detail. You already know that if you take all the locks before you start, before transaction starts execution, before transaction starts execution, what you can do, just take all the locks. Take all the locks before that. Okay, this is called conservative. This is also called conservative 2PL. Yes or no? This is also called conservative 2PL. The another name of this is a conservative 2PL. So in the conservative 2PL, what you do, you take all the locks, each and every lock, take all the locks before the transaction starts. This is approach. In this approach, deadlock will never be possible. If you do this, then deadlock will never be possible. Why deadlock is never possible? Can anyone tell me? In this approach, why deadlock is never possible? In this approach, like why this approach is preventing deadlock? Deadlock will never be possible because you are taking all the resources, so you will never wait for anyone. Do you agree? You are taking all the resources before you start your execution. You are taking all the resources you need, so you will never wait for anyone. So definitely deadlock is never possible. So this is your deadlock prevention scheme. What is another deadlock prevention scheme? What is another deadlock prevention scheme? From your operating system, you tell me. Deadlock prevention scheme, another deadlock prevention scheme from the operating system. Numbering the resources. Yes or no? Correct. Numbering the resources, like what you do, you give a partial ordering the resources. You put a partial ordering the resources. Partial ordering the items, the data items. Correct. Yes or no? You put a partial order on the data items. Putting partial ordering on data items. And then and accessing them only in this order. Accessing items only according to this order. Yes or no? Is this clear? Access them in this order, using that order. So what you do on the data items, all the data items that you have, you put some partial ordering on them. Okay. And after putting this, you access all these items only in that order. Or I can say access items only according to this order, or I can say in that order. Okay, very simple. So in this, what will happen? Let me tell you, like something like this will happen. What you will do, all the logs you will basically, all the data items that you have in your system, all the data items, for example, let's assume data item A, data item B, data item C, data item D. So you will put some partial ordering. Partial ordering, it does not mean that you have to put 1, 2, 3. You don't have to do that. What you can do, you can do something like this. One, if you know that these two things can never be used together, tell me, if you know that these two things, these two items can never be accessed by the same database, by the same transaction, then what you can do? Tell me, if you already know that B comma C, these two items, they can never be accessed by the same transaction. The same transaction will never access both of them. Then what you can do? You can put 2, 2, no problem, 3, and then you can put 3, then you can put 4, something like this. So this ordering you can put on the data items. This is called partial ordering. So what you are doing, you are putting a partial ordering on data items you can put. So this type of partial ordering you can put on the data items. Now what you can do? Now if let's assume this T1 wants to access, this T1 has to access, let's assume, let me assume this T1 needs to access, it needs to access A comma C comma F. Okay, it needs to access A comma C comma F. Then what this T1 will do? Then what this T1 will do? It will access A first. Okay, very simple. It will access A first. First it will access for A, then it will access for C, and then it will access for F. So in this order, it will have to access. So very simple. So what you do? Very simple, that this is the another deadlock prevention scheme. So deadlock will never be possible if you do this. On the data items on your database, you put partial ordering, and then what you do? You access the items only in this order. Only according to this order, you access the item. Okay, is this clear? So in this situation also, what will happen? The deadlock will never be possible. Okay, but of course, see, in this you have to, it is not always possible that you can put the partial ordering. So this approach is also not always possible. Similarly, this approach is also not always possible. This is also not always possible, because sometimes we don't know what are the things I will access. Yes or no? Before starting the, remember, before starting the execution, sometimes we don't know what are the items I will access. Correct? Okay, so this approach is also not practical. Let me tell you, this approach is not used. Also in this approach, there is a problem of starvation, or I can say there is a problem of delay. Starvation, or I can say delay. Your transaction, because your transaction is waiting for all the logs. Your transaction wants all the logs before starting. So it is possible that you will not get all the logs. Okay, it is possible. So that is the reason I can say that there is a possibility of starvation here, and this is not a practical approach, because before starting execution, sometimes we don't know what are the items I will use, what are the logs I will use. So this approach is not practical. This is not used. Let me tell you, this is not practical approach. Also, this approach is good, but this also has many, I can say, many disadvantages, because in this approach, The programmer has to know the ordering. Yes or no? There are many data items, you have to put the ordering, and sometimes it is not possible. And the programmer has to know what is the ordering on the data items. So basically, there are many things here. Now, so these are the prevention scheme we have seen. What is the third one? This is interesting, and most of the gate questions will come from this third one. Okay, now the scheme that we are going to discuss, these are most important schemes. Very, very, very important schemes. So remember these schemes that I'm going to discuss. All the previous schemes were, I can say, those were stupid. Okay, from those schemes, you understood those schemes. These are very easy, but these are the most important schemes, deadlock prevention schemes, which use transaction timestamp, What it means? What this means? Transaction timestamp. What this means? See, when transaction is created, then at that time, at what time it was created? Okay, yes or no? So that time is unique, correct? Two transactions, they have unique timestamp. Yes or no? Because transaction timestamp, what it means? It means basically the time at which a transaction was created. At which a transaction was created. Okay, so you can check the time system clock. From the system clock, in your system there is a clock, tick 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 tick. So you can see from the system clock, you can check what is the time. That time you can assign to the transaction that, okay, this is your time stamp. So time at which transaction was created, this time you can assign to the transaction as the transaction time stamp. So you tell me one thing, if there is a transaction T1, after this transaction T2 was created, then what will happen to the time stamp? This time stamp and this time stamp, what will happen? There is a time stamp of T1. There is a time stamp of T2. What will happen to those? So definitely the old transaction will have less time stamp and the new transaction will have more time stamp. So you can see that this is old transaction and this is a young transaction, younger. This is older. Is this point clear to everyone? What I'm saying? So when a transaction is created, when your transaction is created at that time, at what time it was created? So that time you can assign to the transaction that this is your time stamp. Like your birthday, this is your birthday. Okay, so time stamp is similar to your birthday, I can say. It is similar to birthday. So something like that. So what I'm saying that once your transaction is created, at that time from the system clock, that time you can assign to the transaction, that will be the transaction timestamp. Now you can easily see that if there are two transactions and the transaction timestamp is less than timestamp of this transaction, then definitely this is old and this is younger. Correct? Very simple. So this is the concept of transaction timestamp. Now what will happen? Now deadlock prevention scheme, which will use transaction timestamp. There are two schemes. Let's see one by one. The first scheme is called wait die. Wait die scheme. This scheme, what this scheme says, wait die. The name itself is telling you wait die. You tell me one thing. To whom will you give more priority? Old or younger transaction? Tell me, old or younger transaction, to whom you will give more priority? More priority, like whom to give more priority? Whom to give more priority? Which transaction you should give more priority? Old or younger? The reason, yes, old will be given more priority. What is the reason? Tell me the correct reason. Don't give me this this respect the older ones. Don't give me that reason. Okay, because these are the transactions, these are not people. So tell me, whom will you give more priority? You will give more priority to the older one, but why? Tell me the correct reason. I want the correct reason why we are giving more priority, why we should give more priority to the older transaction. Tell me, one of them you have to abort. older, younger. One of them you have to terminate. One of them you have to kill. Which will you kill? One of them you have to kill. Which will you kill? You will kill the younger. Why? What is the reason? Think about it. What is the reason you are killing younger? Because if it is older, then it has done more computation. Yes or no? If it is older, then definitely maybe it has done more computation. Yes or no? More computation it might have performed. There is a possibility that more computation it might have performed. It might have done. It might have done. Okay, very simple point that if it is old, then more computation it might have done. So definitely this we should give more priority. Okay, now let's see this scheme. What this scheme is saying? Wait die scheme. What this scheme is saying? The name itself is telling you wait and die. Now you tell me, if it is wait and die, who will wait and who will die? Who will wait and who will die? Tell me. In this scheme, who will wait and who will die? So who will wait? Old transaction can wait. And who can die? Who will die? Young transaction will die. Okay, so old transaction can wait and the young transaction will die. Very simple. Now, what this actually says? This actually says that let me assume this transaction Ti wants to access A. Okay, wants to access item A, or I can say want to lock item A. Want to lock item A. This is the point. This transaction Ti want to lock item A, but Tj holds lock on A. Okay, holds lock on A. So there are two transactions. Let me assume that Ti wants to lock on A and Tj holds the lock on A. So there are two transactions. Now you tell me a simple thing. So who wants? So Ti wants to lock A. Simple thing. Ti wants to lock A and Tj holds lock on A. So there are two transactions. Let me assume. Now there are two cases. What is the case one? The case one. If Ti is old, if time stamp of Ti, if that is old, means Ti is old, right? Yes or no? Correct? If this happens, it means who is old? It means who is old? It means this Ti is old. It simply means that this Ti is old. So the person who wants, he is old. So this Ti is an old transaction and it wants lock on A. So what will you do? You will wait this Ti or die with this Ti. Only two options you have, wait or die. Only two options you have, wait or die. This transaction, old transaction wants. Transaction Ti wants. Okay, so this transaction Ti will wait. In this situation, what will happen? In this case one, Ti waits. Okay, Ti waits for Tj to complete. Very simple. This Ti will wait for Tj to release. Very simple. Okay. So in this situation, because Ti wants to lock A and Ti is the old transaction, Tj is holding lock. So Ti is the old transaction. An old person is wanting to lock A, so it can wait. Okay, so Ti, because this is the old Ti, you can see this is the old. So this can wait for Tj to release lock. What is the case 2? What is the case 2? That Ti is younger. Are you getting my point? Ti is younger. Tj is holding, but Ti is younger. Ti is younger. Then what will happen? Means Ti is young. Then what will happen? What will happen to Ti? Then what will happen to Ti? Everything will happen to Ti. Okay, because Ti wants. Tj already has. Ti wants. This Ti wants to lock on A. So Ti is younger. Ti wants to lock on A, but Ti is younger. Then in this situation, Ti aborts. Okay, Ti dies. Ti dies means it aborts. Very simple. So that's it. Is this clear? Mavit, is this point clear? So there is simple approach, wait and die. Who will wait? Old will wait and young will die. Old will wait, young will die. So if old person wants access, then it can wait. If young person wants access, then it will die. Simple. Isn't it simple? Please tell me. Did you understand this? So in this wait die approach, what this wait die approach says, what this wait die scheme says, this scheme says that let's assume item A is already held. Let's assume item A held by some transaction T, held by T. Let me assume. Okay, held by T. So this item A that is already held by T. Simple. Item A, assume this held by T. Now, if younger than T wants to access A, then what will happen? If younger than T wants A, if younger than T, if younger than T wants A, then what will happen? Tell me quickly. If wants to access A, wants to lock A, then what will happen? Tell me. In this situation, what will happen? Younger than T wants to lock A, then what will happen? So this younger will die. Okay, yes or no? This younger will die or abort. This younger will abort. And if older than T wants, wants to lock A, then what it will do? It will wait. It will keep waiting for T to release. Is this understood? Wait and die scheme. Did you understand? So older will wait, younger will die in this scheme. Very simple. Is this understood? Please tell me. Can I go further? Very simple scheme. Now let's see this scheme. This scheme, the second scheme is wound wait. This is the another scheme, wound wait. So tell me, who will wound and who will wait? Who will wound and who will wait? Who will wound? Like, who will wound the other person? Who can wound the other person? One of them will wound the other person. Who can wound the other person? Old can wound the other person. Very good. Okay, very, very, very good. So old can wound. Old can wound. Wound means abort. Old can wound the other person and younger will wait. So you can see younger will wait, younger waits, and older can wound the other transaction. The older can order the old transaction can wound the other transaction. So again, you can notice who is powerful, old or younger. Old or younger, who is powerful? Again, old is powerful because old can wound the other transaction. Wound means abort. Okay, wound simply means abort. Again, I am telling you, wound simply means abort. What this scheme says? This scheme says that, again, assume that this TI wants to lock A. Okay, this TI wants to lock A. And let's assume TJ already holds lock on A. Consider this scenario. Okay, TI wants to lock A and TJ already holds lock on A. Now you tell me what will happen. What is the case one? The case one, the time this TI is the older. I mean, time step of TI is less than time step of TJ. Means basically this TI is older. So the older person wants and the younger person holds. Okay, older person wants, younger person holds. Then tell me what will happen. This older person wants, younger person holds. Then this TI will wound TJ. Snatch from younger. Very good. Snatch from younger. So what will happen? This old TI wounds. Wounds means aborts. Aborts young TJ. Okay, is this clear? So it will wound the TJ. It will wound the TJ. and snatch from him, and snatch from TJ, and snatch lock A from TJ. Simple. So this is your approach. What is the case 2? What is the case 2? The case 2 is that this TI is younger. This TI is younger. The TI wants, but this TI is younger. Can it snatch? Can it wound? Can it roll back the old one? Can it wound the old one? In this situation, this TI waits. In this situation, simply this TI waits for TJ to release. So did you understand both of them? So again, you can notice in this wound wait, what happens? Very simple approach. These are interesting, right? Even reading them is also interesting. Once you understand them, these are very, very, very interesting. What this wound wait says, this wound wait says that old in need wounds, aborts, young in young. Okay, old in need wounds young, and you can notice young in need. If young is in the need, young in need waits for old. This is the simple point. So this is your answer. So please tell me, did you understand both of them? There is a wait die scheme. There is a scheme of wait die. Did you understand this? And there is a scheme of wound wait. In both of them, what happened? In both of them, old is powerful. In both of them, you can notice old is powerful. In both of them. In both of them, who will die? In both of them, who will actually die? Or in both of them, young dies. Yes or no? In both of them, only young will die. In both of them, young dies, means young will abort. Okay. But there is one more very important point in both of them. Extremely important point. Actually, that point you tell me. There is extremely very, very, very important point in these two. Very important point that we did not see so far. So when younger will die, it will again come back. Yes, do you agree? It will again come back. So when a transaction dies, if a transaction aborts, it will again come back. It will be started with new transaction, latest transaction, or it will be started with the original original timestamp. It will be okay when a transaction aborts. Okay, it will restart. It will restart after some time. Okay, it will restart after some time. So the timestamp will be what? The original. Why? What is the reason? Tell me, what is the reason? When a transaction aborts, it will restart after some time, but with the old timestamp, so that it can have more priority. Yes or no? So that it can have more priority with its own old timestamp. With its own old timestamp, so that it can have more priority. So okay, to avoid starvation. To avoid starvation. Do you agree? To avoid starvation. In both these approach, to avoid starvation, this will happen. Just think about it. What I am saying, consider this example. Let me assume these are the transactions, T1, then T2, then T3. These are the transactions. Let's assume this is the timestamp ordering. This is the timestamp ordering. Now what I'm saying that let me assume that this T1 is old. You can clearly see this is old. And this T3 is basically young. Now what will happen? Now let me assume that this T2 will die. Now if this T2 comes with the same time, see, let's assume T3 will die. Let me assume T3 dies. Okay. Are you getting my point? Let me assume T3 dies. If this T3 dies, it comes back after some time and with a new timestamp, then there is a problem. What is the problem? See, what is the problem? See, very simple. I am saying that T1 is there. Let's assume it is executing. Let's assume T2 dies. Okay, at this point of time, T2 dies. Let me assume T2 dies. Now, if T2 dies, now T2 comes back again with a new timestamp, with the latest new timestamp. Okay, new timestamp, new latest. Then what is the problem? Then the problem is this. Now it is again younger. Then again the old person can make it die. Like, okay, it wants. So this T1 can want this. Now between T3 also has come. Now this T3 can want this T2. So are you getting this point? So it will keep, it is possible that it will, this T2, if you keep if you keep giving it new latest timestamp, it will keep become younger. Yes or no? If you keep giving a new timestamp, if you keep giving latest timestamp, then what will happen? It will keep becoming younger. So it will keep aborting, it will keep rollbacking. So definitely starvation will be there. Okay, in this situation, starvation will be there. Are you getting my point? So very simple thing that there are two cases. Case one, what is the case one? Rollbacked, or I can say aborted transaction started with, this is the case one, that aborted transaction, the transaction that is aborting, aborted transaction starting with what? Starting with new latest timestamp. Then what will happen? Then what will happen? It will become younger. It has become younger. Yes or no? It has become younger. Aborted transaction T, then T has become younger. You can notice then T has become younger. Again, less priority. Then T has become younger. Younger means less priority. Younger means less priority. So T has become younger. So what it means? It means that it is possible T, okay, possible T1 will, T will again roll back. Possible T can again roll back. Again abort. Okay, if you keep doing this, it will keep aborting. So this key T may keep aborting. T may keep aborting. So in this situation, I can say starvation. Yes or no? This is called starvation. So in this case one, what we got? In this case one, we got starvation. We got starvation. Okay, very simple. Now in the case two, what is the case two? What is the case two? That you, or aborted transaction is starting with its original timestamp. Its original old timestamp. Okay, aborted transaction T, it is starting with its original old timestamp. Then what will happen? Then this T is older. Then this T has become older. Yes or no? Then this T is older now. So more priority. So this T has more priority now. If it has more priority, then definitely I can say no starvation. Okay, so in this situation, there is no starvation. So very simple. This is the complete analysis of this topic. Please tell me, did you understand? So remember this by default, this wound wait and wound die. This wait by default, this wait die, in this wait die approach, or whether you take wound die, wound wait approach, whether you take this approach, or whether you take this approach, in both the approaches, what will happen? In both the approaches, in both of them, I can say in both of them, aborted transaction starts with what? Tell me. Aborted transaction starts with its original old timestamp to avoid starvation. Simple. This is your complete explanation of this topic. I hope you understood this. So you have wound weight and weight die and wound weight. Now, which of them is preemptive? Like, which of them is preemptive? Weight die? In which of them preemption is possible? Preemption. In which of them preemption is possible? Yes, in this you can preempt, because wound means you are preempting, right? Yes or no? Wound simply means preempt, you are preempting. Preempt and abort. This is what wound says. So here you can see this approach. This is a non-preemptive approach. This approach is non-preemptive. Like, we don't disturb the person who is executing. Okay. Non-preemptive means don't disturb the person who is executing. Don't disturb executing transaction. Okay. Executing transaction, like the transaction that is already executing. So don't disturb it. But this is preemptive. This is preemptive because the old person can preempt it. Okay, is this clear? Very simple. This is non-preemptive. The person who is executing the transaction, who is executing, don't disturb it. Okay. Yeah, it is possible that, of course, it is possible that I myself can preempt, or I myself can kill myself. Okay. in this suicide is possible. Like, you can see that if the younger transaction is younger transaction wants the data, wants to log the data which is already taken by the older transaction, then the younger transaction will die. But that is not preemption, right? Yes or no? We are not preempting anyone. Is this clear? So here the younger transaction will die, but that is by himself, by itself. The younger transaction will die by itself. No one is killing it. It will kill itself. Okay, so there is no preemption. Similarly, but here you can notice the old transaction will abort the younger transaction. So here this is preemptive and this is non-preemptive. So this is your chapter. I hope you understood the complete chapter. All the preempts, weight die, the wound weight. Okay, all these things we have already seen. And this is an important point, that both in weight die and wound weight scheme, a rolled back transaction is started with original timestamp. The older transactions thus have precedence over newer ones and starvation is avoided. This is important. So this is the complete chapter that we have seen. Now, one last thing is remaining, but before that, you can see basically what is happening. The younger transaction is saying this. Okay, correct? I can say the younger transaction. We can say the younger transaction has this situation. The younger transaction in the weight die or wound weight. Okay, so definitely you are basically killing the younger transaction every time. Very simple. Okay, so that's it. Now, this you already know, deadlock detection in the operating system you have already seen. What you will do? Like, if you don't have deadlock prevention, so far we have seen deadlock prevention, correct? So far, what we have seen so far, we studied deadlock prevention. We studied deadlock prevention. This is what we studied. But these are expensive. These deadlock prevention, these are actually, we don't apply them in the real life. So far we have studied deadlock prevention. Prevention means deadlock will never occur. So is there anything to check? Is there anything to check? Please tell me. Deadlock will never occur. Is there anything to check? Is there anything to detect? Will never occur. So in this situation, there is nothing to check. You never have to check. There is no detection required. So deadlock will never occur. So no detection required, I can say. So no detection required. No detection required. Okay, no deadlock detection required. No deadlock detection required. But if we don't apply this, then what will happen? If we don't use this deadlock prevention, then what will happen? If we don't implement, this deadlock prevention, then what will happen? Then deadlock will be possible. Correct? Okay. So if we don't implement this deadlock prevention, then deadlock possible. If deadlock possible, then what you will have to do? Then deadlock will be possible. Then periodically you will check for detect deadlock. Yes or no? Then what you will do? You will periodically you will detect deadlock. Detect deadlock and then recover. And then recover. Recover means kill one of the transaction. Okay, very simple. So for deadlock detection, this is the next topic, that is deadlock detection. For deadlock detection, what you can do? In the operating system, what you do for deadlock detection? Tell me, in the operating system, for the deadlock detection, what you do? You create a graph, resource allocation graph in the operating system. A resource allocation graph you create. Here you what you do? In this you create something called wait for graph. So for deadlock detection, what you do? Let me tell you. This deadlock detection. For this deadlock detection, we create a wait for graph. This wait for graph we create. Okay, wait for graph. Wait for graph is created. Okay, this graph, the name of the graph is wait for graph. This is created very similar to the, in this graph what happens? Who are the nodes in this graph? Who are the vertices? Who are the nodes? The nodes are the transactions. The nodes are the transactions. Which transaction is waiting for whom? So these are the nodes. And you can notice this age. When do we put this age? Ti to Tj. This age is put. When do we put this age? This age we put when Ti is waiting for Tj. Okay. This we put, it simply means, this age means that Ti waiting for Tj. Okay, this Ti, this is a waiting for Tj. This Ti is waiting for Tj. So very simple. So this is the graph that we create, and every transaction, remember it's like this. A transaction is there, then this is the transaction, then this is the transaction. This type of graph we create, that let's assume T2 waiting for T3, T3 waiting for T1, and let's assume T2 waiting for T1. You tell me, in this, do we have a deadlock? This is a wait for graph. This graph is called wait for graph. The name of this graph is wait for graph. Is there any deadlock in this graph? There is no deadlock. Why? See, you can see that T2 is waiting for T3, T2 is waiting for T1. But you can notice T1 is not waiting for anyone, right? Yes or no? Array C. T2 cannot happen because T2 is waiting for T2. T2 is waiting for T1. This T2 is waiting for T3. So we cannot execute T2. T2 cannot be executed. T3 cannot be executed because T3 is waiting for T1. But T1 can be executed. It is free to execute. Yes or no? It is free to execute. So what will happen? You can notice T1 can execute first. Then who can execute? Then T3 can execute. Then T2 can execute. So like this, they can execute. This is the execution order. Yes or no? So this is the execution order. So definitely I can say that no deadlock. I can say there is no deadlock because T1 is free to execute. T1 is not waiting for anyone. T2 is waiting for T3. T2 is waiting for T1. T3 is waiting for T1. T1 is free to execute. It can execute. So this is the execution order. Now you tell me about this one. If I do this, then what will happen? Now T2 waiting for T3. T3 waiting for T1. T1 waiting for T2. Then this is called deadlock. Deadlock. This is the situation of deadlock. So deadlock will possible if and only if wait for graph has cycle. Okay. Deadlock is there if and only if. This is if and only if statement. This is very important. So the system is in deadlock. The system is in deadlock state if and only if. If and only if the wait for graph has a cycle. In the wait for graph, you have a cycle. This is if and only if. Means if you have cycle, then there will be deadlock. If you have deadlock, then there will be cycle. So this is your very simple algorithm, that what you do, you create this. Tell me, this graph is dynamic or not? This graph, this wait for graph, is this dynamic or static? This wait for graph, this is dynamic. It is dynamically changing. This is dynamically changing. Remember, this is dynamically changing. What it means? It means that let's assume many transactions are executing. A lot of transactions are executing. Hundred thousands of transactions are executing. Okay. So this graph is actually dynamically changing. Remember this wait for graph. Like let's assume at initially T1, T2, T3 are there initially. After some time, what happens? After some time, T1 waits for T2. After some time, after 1 hour, T2 waits for T3. After 1 hour, T1 does not wait for T2. After 1 hour, T1 waits for T3. After 1 hour, let's assume T2 waits for T1. After 1 hour, this does not happen. T2 does not wait for T3. Are you getting my point? Is this clear? So the wait for graph is dynamically changing. We dynamically keep putting the edges and we dynamically keep changing this. So this is actually dynamically changing. Whenever T1 is waiting for T2, then you put the edge basically, okay, whenever. Very simple. Whenever, at any point of time. Remember, at any time. At any time. If Ti waiting, if Ti waiting for Tj, then what you do? Then what you do? Tell me. If Ti waiting for Tj, then put edge. Then put Ti to Tj edge. This edge you put. Okay, then just put this edge. And at any point of time, whenever Ti is not waiting for Tj, okay, Ti no longer waiting for Tj, then you remove this edge. Then you remove this edge. Okay, so this is dynamically changing this graph. Finally, you can see, tell me which of these graph is in deadlock, which of this system is in the deadlock, this system or this system? Which system is in the deadlock? So you can clearly see in this system is not in deadlock because who is free to do? Tell me which transaction is free? Which transaction is free to happen? You can notice T17 cannot happen because T17 is waiting for T18, T17 waiting for T19, T19 waiting for T18, T18 waiting for T20, but T20 can happen. First, this can happen, then T18 can happen, then T19 can happen, then T17 can happen. Similarly, but here you can notice there is a cycle. There is a cycle in the graph. So this is the system is in the deadlock because there is a cycle in the graph. Okay, very simple. Now you tell me, is this system in the deadlock? This is my question. Let's assume I give you wait for graph. The wait for graph is like this: T1, T2, T3. Is this system in the deadlock? Tell me. This system is in the deadlock or not? Look at this system and you tell me, is this system in the deadlock? Like consider this system. Is this system in deadlock? Is the system deadlocked? Again, the answer is yes. Okay. Yes, the system is deadlocked. Remember, as I told you, do we require all the transaction to in the deadlock? Do we require all the transaction in the cycle? Do we require that? Do we need all the transaction in the cycle? Do we need that? I did not say that. I did not say that. I said that in the wait for graph, there exists a cycle. Yes, there exists a cycle. So this is system deadlocked. Okay, this is what we are saying. We are saying that the system is deadlocked if and only if we have a cycle. We are not saying that all the transaction must be in the cycle. Okay, we are not saying that all the transaction must be in the cycle. Of course, these two can happen. This can happen, this can happen. But this is a deadlock because these three people are, you can see this set of transaction, they are waiting for each other. So definitely this system is deadlocked. Okay, yes. So very simple. Let's see this question. Tell me the answer for this quickly. Very quickly tell me the answer. Which of these? So complete, given the graph below, wait for graph is given to you. You don't have to read this. You already know this. This you already know. Don't worry. This is just the description. This is just the definition of wait for graph. Okay, tell me which graph is deadlock free? Which system is deadlock free? So you can see that this system is deadlock free. This system is not deadlock free. Just look for cycle. Okay, this system is definitely not deadlock free, right? This system is not deadlock free. And you can see that this system is deadlock free. There is no cycle. What about the third one? What about the third one? There is a cycle. There is a cycle. There is a cycle. Okay, in the third, you have a cycle. So there is a cycle, you can check. You can check there is a cycle. So because we have a cycle, so definitely this is not deadlock free. Okay, what about the next? Again, there is a cycle. So this is also not deadlock free. There is a cycle. So this is also not deadlock free because there is a cycle. Okay, so very simple. Deadlock free means there is no cycle. Deadlock free means acyclic, wait for graph. Okay, very simple. So the answer will be only option 1. Okay, now let's move on. So this is your chapter, and whenever you detect a deadlock, then what you will do? Whenever you have detected the deadlock, then what you will do? Kill one of the transaction. Which one? Kill one of the transaction. Which one? Which one? Whenever you have detected the deadlock, then you will kill one of the transaction. Which one? Yes, the transaction which had done less computation. We will prefer to kill that transaction. So when you can easily see that basically once you are in the deadlock, if the system is already in the deadlock situation, then some of the transaction you will have to abort. Which transaction we have to abort? Which transaction we have to abort? That is called victim selection. That is called victim selection. Like which transaction to kill, whom to kill. We are deciding whom to kill. Then generally what we do? Generally we take the transaction which is running for small time, I can say. Generally, we avoid selecting the transaction which has been running for long amount of time, means it has done lot of update. So what we do, we select the transaction that has not made many changes. The younger transaction we select. Okay, we can select the younger transaction, we can select to kill. So one of the transaction we will kill. Which transaction we will kill? We will kill the younger transaction because it has not computed, it has not done many computation. Okay, so this transaction we will kill. Very simple. And how to handle the starvation? Tell me, this wait die and wound wait, are they handling the starvation? Wait die approach and wound wait approach, are they handling the starvation? Are they avoiding the starvation? Of course, they are avoiding the starvation, right? In the wait die and wound wait, there is no starvation, right? Because you are also, there is no starvation, correct? Because once you abort a transaction, then you will start it with its original old timestamp. So there is no starvation, that we have already seen. Mavit, correct? We have already seen that in the wait die, in the wound wait, there is no starvation. They handle the starvation. What is another approach for handling the starvation? Like when you have, tell me, when you are aborting a transaction too many times, another approach is FCFS, first come first serve. Yes or no? If you want to handle the starvation, then you can apply the first come first serve approach. Correct? Yes or no? Okay, first come first serve approach you can do, so that you can handle the first come first serve on the transaction. The transaction who is older, you execute it. Okay, basically if a transaction is waiting for a long time, you execute that. So this type of techniques you can apply. Anyway, we have already seen this. Now let's move on. That's it. So now we only have the gate questions to do. Can I give you these questions as a homework? See, there are many gate questions on this topic. The topic that we have seen on this topic, there are many gate questions. Like you can see, this is a gate 2016 question. This is gate 2004 question. All these questions are on the same topic. On the same topic. All these questions. This is another gate question on the same topic. This is another gate question on the same topic. Can you notice there are a lot of gate question on the same topic? So can I give you these questions as homework? This question, this question, this question, this question. So try them. I have full confidence on you. You will be able to do. We will discuss in the next class, but don't worry. You can do these questions easily. You can do. Okay. I have full confidence on you. Okay. So this is your chapter. We have done two-phase locking. 2PL is over. Variations of 2PL is over. Deadlock handling over. Wait for graph over. Weight die, wound weight, these approaches, they are over. So basically, almost your DBMS is over. Almost DBMS is over. Let me tell you. Most of the DBMS questions are from whatever we have seen so far. Okay. So now at this point of time, you can try all the test series questions. Okay. Ekta, Mavit, this is a suggestion to all the Go classes students that now you can attempt at this point of time, you can attempt Go classes test series.